In Cycle 2, Lesson 7, we're going to revisit rates of change. This time we're going to look at trigonometric functions, and a little bit later on in the lesson we're going to look at rates of change in logarithmic functions. So remember that the instantaneous rate of change is the slope of a line, a tangent line, a line that touches a curve, any kind of function, whether it's trig or log or anything else, polynomial, rational, you name it. It's the slope of the tangent line. That's instantaneous rate of change. So you find the tangent line at a particular point, and then you get the slope of it. Average rate of change was the other thing we've looked at, and that's just the slope between 2 points on a curve. And we use the slope formula for that. So let's start with instantaneous rate of change for a trig function. So we want to find it all along a sine curve. So let's just quickly remember or remind ourselves what a sine curve looks like. It has, if we say that, let's say this is 1 and this is -1, sine starts at 0, 0, pi over 2, 1, pi 0, 3 pi over 2, -1, and 2 pi 0. Connect the dots, and we get a nice curve. Now, if I want to calculate the rate of change, we know that there's probably the best way to do it is to use the formula called the difference quotient. So this is y equals sine x. And we can do that, again, by adding a very small interval, or subtracting a very small interval from x and subtracting a very small interval from our x value, and then doing the slope formula of it. So IRC, let's just do it for 0. Let's start with 0 for this table here. And so then we would have IRC is equal to, and again, it's y2, it's still the slope formula, y2 minus y1 over x2 minus x1. So I think that's good to remind ourselves of. So let's say we want to find it at this instantaneous rate of change at 0, then the x's are the easiest part. If I just do 0 minus a very small interval, which would be 0. I've been using 0.001 as my interval, so 1/1000th of a unit. And so that could be my x. Actually, x2 would be the bigger one, so I'd make that plus, and then subtract 0 minus 0.001. So it'd be, again, I'll come back and do the top in a second. So I just wanted to show where everything comes from, but really it's just going from 0.001 minus negative 0.001. And the two minuses are going to make a positive, and I'm still just working on the bottom. So we're going to end up with 0.002 on the bottom here. As far as the top goes, we're using the function as given. In this case, it's y equals sine x. So I would do sine x, well, x is 0.001. So sine of 0.001 minus the sine of x1, which would be negative 0.001. Again, I already calculated those on the bottom here. So I'm just getting these values. This one I'm just plugging in here, and this one I'm just plugging in here. Those are my x values. Well, actually, the whole thing is my x value, but when I simplify it, it's the same thing. And when I take the sine of positive 0.001, I get 0. I'm gonna write it a whole bunch of decimal places because we're working with such small numbers that it's important to carry a lot of decimal places. So it's 0.000, not too many zeros. I think it's just 3 zeros and then a bunch of 9s. And then if I do the same thing, if I take the sine of negative 0.001, then it turns out to be negative 0.000, and then a bunch of 9s again. And we can just do this on our calculator. We make sure our calculator is set to radian mode because we're working in radian mode for everything in this course for the most part. And these are just the numbers our calculator crunches out for us. When I simplify that, again, these two negative signs here simplify to become a positive, just the way these ones simplify to become a positive. And so then what I end up with is really adding those two together, and I get 0.001 and then a whole bunch of 9s. And then the last step is I divide 0.00199999 by 0.002, and it works out to be 0.99999, etc. So there's more, but basically this is approximately equal to 1. So what all this work showed using the difference quotient formula is that the slope of the tangent line at an x value of 0 is 1. So this is not, this part here, pay attention to what this column heading is. It's not our y value. This is just not our y output. We're looking at the slope when x is 0. So this is not a list of ordered pairs. Anyway, so the slope when x equals 0, the slope of the tangent line, which is the instantaneous rate of change, at 0 is 1. So if I was to draw the tangent line on here, I can give it a shot here. The tangent line would probably look kind of like this at 0. That's got a slope. I was forgetting, actually. I was just using the grid to help me eyeball it, but I was forgetting that on the x-axis we're not going up by 1s here. So maybe, just to make things a bit more accurate looking, let me just redo that considering the appropriate value here. So pi over 2 was actually about 1.5, which means that 1 would be more like somewhere, it's around the same area. All right, I'll stick with that. That would still be approximately a slope of 1. So that's a tangent line there. Now, we want to find the point. We're going to fill in all these different points along the graph. That's a lot of calculating. So instead of doing that, I've got a Desmos program which will show us how that works. You can see already, actually let me drag it back. If you look at line 4 here, counting them as 1, 2, 3, 4. When I get to line 4, you can see that C is set at 0. You can see we have this tangent line here at 0. And if you look at line 5, it says in the bottom right, m equals 1. So that's where we're going to look for the slope. So all this stuff is just giving us our, a different way of looking at the slope. So let's just illustrate. Let me just let it run for a second. You can see as we move along the curve, we're getting tangent lines that get less steep until they get to the top, and then they start becoming negative, and then they start to, once they get to the minimum point, they go around and they start over again. So let me drag this back to 0. And so to fill in the table of values, the next point, I think the next one was pi over 6. Okay, so I've got this actually programmed so that it goes up by units of pi over 6. So this is pi over 6 here. Again, look at line 4. It says 0.52359, a whole bunch of decimals here. But remember, pi is just a number. If I were to actually divide pi by 6, I get that same number, 0.52359, etc. So pi over 6 as a decimal is 0.52359. So here's the point where x is pi over 6. Here's the tangent line at that point. Notice how the slope is a little bit less. Instead of being 1 now, let's round it to 0.87. Now, the way this program is set up, it's going to skip over pi over 4, which is the next one in our table. So the next one would be, it's going up by pi over 6, as I already said. So the next stop on our graph here would be 2 pi over 6, which reduces to pi over 3. Pi over 3 is a decimal, is 1.047, or let's call it 1.047. 0.05, and you can see the slope is 0.87 here. Nope, sorry, I'm looking at the wrong place. I was looking at the y coordinate. I've got to keep my eyes on the slope, again, which is in line 5, m equals 0.5. So 0.5 for this one. Again, skipping over pi over 4 for now. Let's try pi over 2. Now you can see that it's a perfectly horizontal tangent line, which means it's got a slope of 0. And then 2 pi over 3 would be the same as 4 pi over 6, so that would be the next stop along the path here. Clearly we've moved into a negative slope for the tangent line now. It's negative 0.5. So we got this symmetry going on. And that means that we can probably start to predict, again, I'll skip over the one with the base of 3 pi over 4, but 5 pi over 6 I'm going to predict is negative 0.87 as my slope of my tangent line. Let's just confirm that. And it is. And then at, I think I went past the next one I wanted, at pi exactly, we're back to a slope now of negative 1. And so it's just going to keep repeating, which is good to know because then we can save ourselves some more time. This is going to be negative 0.87, skip the pi over 4, then we'll have negative 0.5, and we'll be back to 0 at 3 pi over 2. But let's let it play out for a little bit and see if that happens. I'll stop it there at 3 pi. Oops, no, I didn't stop it. Drag it back. Okay, finally, got it. Okay, at 3 pi over 2, which is, as you can see, there's the x-coordinate, we got a slope again of 0. Then it goes around the curve and starts getting positive again. We get a slope of positive 0.5, 0.87, and so on. So the only thing that I didn't really get on here was the ones that were pi over 4 because they didn't fit my pi over 6 intervals. Turns out, just to save us some time, pi over 4 has a value of approximately 7.1. So 3/4 pi over 4 is the same, except going in a negative direction, our line. This one's still going to be negative. And we could keep going until we got to 2 pi if we wanted to. But you can see, let's draw a few other tangent lines in here. So at, for example, pi over 2, we had a perfectly horizontal tangent line. So the tangent line looked like this. And at pi over, let's say 2 pi over 3, we had a negative 0.5. So 2 pi over 3 is the same as 4 pi over 6. That one should be about here. And I'm making that too steep. Let's try again. Should be less steep, so it'd be more like this. So about 0.5. And so on as we go around the curve. So we can use Desmos, we can see how the instantaneous rate of change changes as x moves along. And we can, if we ever want to calculate a specific point, we could always use this formula. Again, that's how I came up with 0.71 for pi over 4, is I just put that in for x into the instantaneous rate of change formula here. I took pi over 4 and I added 0.001, I subtracted 0.001 and did the difference quotient. Okay, we can also do this for log functions. Although for these examples I won't do a Desmos demonstration, I'm going to stick to just our formulas, but it works. We can still get regular average rate of change, we can get instantaneous rate of change, all of the same things apply. So here's an example. Bacteria culture of 20 doubles every 15 minutes given by the equation n at t equals 20 times 2 to the exponent t over 15. So n would be number of bacteria, t is time in minutes. So the 20 is our initial value. The doubling tells us our growth rate, which is the base of our exponent. The 15 minutes is our doubling time. So you can see how if you put different times in for t, it'll double a certain number of times. So if after 15 minutes, if I put 15 in for t, then I'd have 15 over 15 for my exponent, which would give me 2 to the 1. It would double one time. If I put 30 minutes in for t, then 30 divided by 15, and the exponent becomes 2. So I'd have 2 to the exponent 2. It would double twice, and so on. Okay? Not doubling times, doubling time, 15 minutes. Determine the average rate of change between 2 and 5 minutes. So again, for average rate of change, what we want to do is we want to use the slope formula, but we don't have to use that small interval of 0.001. We just can do y2 minus y1 over x2 minus x1. Well, this is x1, this is x2, so that's easy, that part. 5 minus 2. And I just have to find out what the y value, in other words, n at 2 and n at 5 is. N at 2 is going to be 20 times 2 to the 2 over 15. Let's make this bigger. That works out to 21.936. I'm going to round it to 3 decimal places. I don't have to carry as many decimal places when I'm doing average rate of change. Really important to carry a lot of decimal places for instantaneous rate of change. Average rate of change is not as big a deal. So for this one, 20 times 2 to the exponent, 5 over 15, which works out to be 25.198. So this is my y2 here, this is my y1 here, and so 25.198 minus 21.936. That works out to be 1.087 approximately. So the average rate of change, I wouldn't want to carry that many decimal places in my final answer. I just want to have them as I go along. But I could round that a little bit and I'd say maybe it's about 1.1 bacteria per minute. Now, if I want to find the instantaneous rate of change at 3 minutes, this is where I have to get back to using that plus or minus 0.001. Still using the slope formula, as we already saw, but now IRC, but now it's using plus or minus 0.001. So if it's at 3 minutes, that means that if I add 0.001 to 3 minutes, then I've got 3.001 minutes. And if I subtract 0.001 from 3 minutes, I get 2.999. Those are my x1 and x2, but not in that order. So then I want to find n at 2.999. And that, of course, is going to be figured out by doing 20 times 2 to the 2.999 over 15. Now, I do need to carry a lot of decimal places again here, because the difference between 2.999 and 3.001 is not going to be much. They're going to look exactly the same for the first few decimal places. So I get 22.9729055. If I do the same thing for n at 3.001, it works out to 22.97502875. As you can see, the first few decimal, or couple decimal places actually are identical. It's not until I get to the third decimal place that these two things are different. That's why it's really important to carry all these decimal places. So these are the y2 and y1. I need to put them into the appropriate place. And when I crunch the numbers and work it all out, following order of operations, of course, I get 1.06 bacteria per minute. Last example, given f at x equals 3 log x plus 2, determine the instantaneous rate of change when x equals 3. So it's really the exact same idea as what I just did, except my function that I'm looking at is now this logarithmic function instead of this exponential function. Not going to do anything different whatsoever. So at 3 minutes, we've already seen that we want to have x values of 3.001 and 2.999. And as far as the top goes, sometimes if I want to do it all together at one thing, I'll just write it like this. I'll take the formula, I'll go 3 log, and then I'll put in the 3.001 plus 2 just to show what I'm doing here. And then, of course, 3 log 2.999 plus 2. And I can actually type this all in my calculator at once if I'm skillful at it, if I'm careful about order of operations. Then I could do it all in one shot, and what I get is 0.0005 divided by 0.002. It's always going to be 0.002 on the bottom if I use a decimal, an interval of 0.001. And when I divide that out, I get 0.26. I don't know what this log function defines, so I can't really give units for it, but this is the instantaneous rate of change on this log function at 0.26. Maybe I could just finish off by graphing this, seeing what this log function looks like. Let's just go for a new graph. Y equals 3 log x x plus 2. Okay, so there's 3 log x plus 2. When x equals 3, there's their point of intersection. The y-coordinate is 2.097, but again, don't get confused by that. That means nothing. Just imagine a tangent line in there with a slope of, what was it, 0.26, about a quarter of a unit. So imagine a tangent line. We can see that the tangent line is going to be going up to the right. The slope isn't that steep, about 0.26. Fits with what we calculated. So again, it all fits together.